Let's start Chapter 3, Primal Dual Splitting Methods. The goal of this chapter is to study techniques for deriving primal dual methods. Primal dual methods are methods that explicitly maintain and update both primal and dual variables for the primal dual optimization problem pair. The base splitting methods that we have seen in the previous chapter, when they are applied directly, they are limited to optimization problems of the form of minimizing f of x plus g of x or f of x plus g of x plus h of x in the case of dys. Primal dual methods that we will see in this chapter can solve a much wider range of problems, and they can exploit problem structure with a much higher level of freedom. The sections of this chapter are organized based on the techniques that we use to derive the various methods. The first technique that we'll talk about is called the Infimal postcomposition technique. The Infimal postcomposition technique, which name admittedly does sound a little bit intimidating, involves these two steps. In the first step, we take an optimization problem of this form, where we minimize with respect to a variable x, and the objective is expressed as a sum of functions. Here we just write down the first one, f, and then the constraint set is, the constraint is defined by this type of linear equality constraint. We take an optimization problem of this form, and then we transform it into an equivalent form without constraints involving the Infimal postcomposition. This thing is referred to as the Infimal postcomposition of f by a, and by using this function and changing the variable from x to z, we are able to remove the linear equality constraints. We will further discuss the definition of the Infimal postcomposition and this equivalent transformation in the following few slides. Once we transform our problem, originally with linear equality constraints, into an equivalent problem without any constraints, we can then apply one of our base splitting methods. These two steps constitute the Infimal postcomposition technique. The Infimal postcomposition of f by a is defined in this manner. We abbreviate the word Infimal postcomposition to IPC. So the IPC of f by a is a function of, in this case, the variable z. Once the variable z, the input z, is specified, the value of IPC of f by a of this function is defined by this minimization, by this infima. We minimize the function f of x subject to the constraint that x satisfies the linear equality constraint ax is equal to z, where again z is the input to the IPC function. To clarify, here the original function f takes in as input x, and x has length n. The matrix A is an m by n matrix, and the input to the IPC of f by a, is the z input, is of length m. So the length of the size of x and z, they do not need to be equal, but the matrix A needs to have this dimension m by n in order for all the dimensions to fit. The IPC of f by a, so this function, is also referred to as the image of f under a. If the function f is CCP, and if this regularity condition holds, then the IPC of f by a is also a CCP function. Let's discuss two identities involving the IPC. These identities explain why it is that the IPC function arises. The first identity is that if we take the IPC of f by a, this function, and take the conjugate function, and then provide u as the input, that is exactly the same as taking the conjugate of f and then providing a transpose u as the input. In the previous chapter, when we were discussing primal minimization problems that had linear equality constraints, the corresponding dual maximization problems often had functions of this form. Therefore, this relationship explains why it is that for minimization problems with linear equality constraints, the IPC function naturally arises. Let's derive this identity. So we take the IPC function of f by a and take the conjugate. Well, to do so, we directly apply the definition of the conjugate, where the input to the conjugate is u. So we have u inner product x, where x is the optimization variable. And here we just plug in the definition of the IPC function. Remember, the IPC function is defined through this infimum. Next, we convert this supremum into an infimum by flipping the signs and pulling out a negative sign to the front. And then we note that this infimum is the infimum with respect to x, and this term has nothing to do with x, so we can put this term inside of this infimum. And then after that, we have a double infimum, so we can just combine the two infimums into a single infimum with respect to both x and the z variables of this expression. Note that this term is entered into here. And then finally, now that we have a double infimum, we can perform the infimum over the variable z before we perform the infimum over x. So then if we take the infimum over z, this indicator function fixes the value of z to be equal to a times x, so we can replace the instance of z with ax and get rid of this indicator function. Now that we have this expression, well, this expression with the negative sign in front is exactly f star with a transpose times u. So this first IPC identity explains why it is that the IPC naturally arises from minimization problems subject to linear equality constraints. Next, we have the second IPC identity. The identity states that under this regularity condition, the proximal operator with respect to the IPC of f by a can be evaluated by first performing this minimization problem and then computing this matrix vector product. Remember, this regularity condition, which states that this intersection is not the empty set, ensures that the infimal postcomposition of f by a is a CCP function. And when IPC of f by a is a CCP function, then this proximal operator is well defined. The second IPC identity, this current identity, is also stating that if when this regularity condition holds, this argmin, the argmin defining the x, exists, and therefore the output z is well defined. This equivalence is also implicitly stating that although the minimizer x is not necessarily unique, it does exist, but the x is not necessarily unique. Regardless of which x we choose, once we multiply by a, the output z is uniquely determined. This identity is established as exercise 3.1 of the book. Let's use the IPC technique to derive the alternating direction method of multipliers, which is commonly abbreviated to ADMM. We consider this primal problem, the primal problem of this form, where we minimize f of x plus g of y. The optimization variables are x and y, and note that x is length p and y is length q, so the lengths of x and y, they do not have to match. The x variable and the y variable are coupled through this linear equality constraint. The equality constraint reads a of x plus b of y is equal to c. To clarify, the c vector is of length n, so the matrix A is an n by p matrix, and the B matrix is an n by q sized matrix. This primal problem has a corresponding dual problem where we maximize with respect to the variable u. U is of length n, and the objective function is minus f star composed with minus a transpose minus a g star composed with minus b transpose and a linear term minus c transpose u. This primal dual problems pair is generated by this Lagrangian. So the Lagrangian has the primal variables x, y, and the dual variable u. And the L is f of x plus g of y, and then u, inner product with ax plus by minus c. This Lagrangian is convex in x and y. It is jointly convex in x and y, and it is linear and therefore concave in the dual variable u. We assume these regularity conditions. We will discuss these regularity conditions further soon, but one immediate consequence of these regularity conditions is that the IPC of f by a and the IPC of g by b, those become CCP functions as a consequence of these regularity conditions. Finally, when we describe the algorithm, we will be using this augmented Lagrangian. So the augmented Lagrangian in general is an object that is considered broadly throughout the optimization literature. In our derivation of ADMM, we'll observe that the augmented Lagrangian arises quite naturally. The augmented Lagrangian is defined as this first part, which is just the Lagrangian, with this additional penalty term. This penalty term, scaled by rho, penalizes the deviation from penalizes the deviation from the linear equality constraint. The augmented Lagrangian is named so because it is defined as the Lagrangian with the additional penalty term. To derive the ADMM method, we will take this primal problem and then apply the Infimal postcomposition technique, the first step of the IPC technique, to transform this constrained minimization problem into an unconstrained minimization problem. So the way we do so is, given this original primal problem, we introduce this additional z variable. So we say ax is equal to z. So now z is this added, a new additional optimization variable, but then we have z plus by is equal to c. These two problems are clearly equivalent. Then in the next step, what we do is we minimize with respect to the x and the y variables while keeping the z variable as is. In this optimization problem, the only part that involves the x variable is this objective term and this linear equality constraint. And the only part that involves the y variable is this objective term and this linear equality constraint. So essentially, we can deal with this objective function and this linear equality constraint separate from the other parts. So once we do that, we get the Infimal postcomposition of f by a as a function of z. And then if we minimize with respect to y here, then we get the Infimal postcomposition of g by a, and then we provide as input c minus c as the input. We'll define this first function as tilde of f, and we'll define this function as tilde g. We now have a convex minimization problem that fits the form of Douglas-Rackford splitting. The optimization problem is minimized with respect to z, the objective function f tilde plus g tilde. So now we are ready to apply the Douglas-Rackford splitting fixed point iteration with respect to the proximal operator of g tilde, and the proximal operator of f tilde. A minor technicality is that in order for the scalar factor alpha to appear nicely in the final result, we'll be using alpha inverse and alpha inverse as the resolvent step size, as the proximal operator's step size, rather than just alpha itself. So we perform the fixed point iteration, but we will define the iterates as not as z, but we will define zeta as our main iterates. So the Douglas-Rackford fixed point iteration maps from zeta k to zeta k plus 1. But otherwise, this is exactly the same as the DRS that we had seen. The outputs of the proximal operators are referred to as the zk plus 1/2 and the zk plus 1 iterate. And so to obtain zeta k plus 1, we have zeta k plus zeta k plus 1 minus zeta k plus 1/2. So this three-line expression of the DRS FPI is correct, and we know that the DRS FPI converges to a fixed point if a fixed point exists. But the proximal operator with respect to g tilde and f tilde are not really friendly things, so we want to simplify this iteration into a form that is more recognizable, more easily recognizable. So what we do is we perform a change of variables. So we define a zk plus 1f to be equal to c minus byk plus 1. So since zk plus 1/2 is given, we are defining yk plus 1 implicitly in this manner. And then we define zk plus 1 to be equal to axk plus 2. And we define zeta k to be alpha 1 over alpha times uk plus a times xk plus 1. And then, in order to simplify evaluate the proximal operator with respect to the IPC functions, we use the second IPC identity that we had discussed previously. So plugging this all in and simplifying things out it requires some amount of work, but when you carry this out, the result is this. So in order to obtain the yk plus 1 update, we need to solve this minimization problem. In order to obtain the xk plus 2 iterate, we need to solve this minimization problem. And then finally, to obtain the iterate uk plus 1, we need to perform this update. Now note that here we defined zk plus 1f in terms of the yk plus 1 iterate, but we defined the zk plus 1 iterate in terms of the xk plus 2 iterate. And as a consequence, when we substitute everything in, this three-line expression of the DRS FPI becomes this three-line expression where we have the iterate yk plus 1, and then xk plus 2, and then uk plus 1. Now this choice of indexing is somewhat intentional, and now if you note that in the xk plus 2 update, the xk plus 2 update depends on uk plus 1 and yk plus 1. So the yk plus 1 update iterate was computed in the previous step, so that's fine. But the uk plus 1 update is supposed to be computed in the next step, so the dependency of these iterates is not correct. And also the uk plus 1 iterate depends on xk plus 1. It does not depend on xk plus 2, so it's perfectly fine for us to swap the order of these two updates. So then once we swap the order of these two updates, the order of the updates becomes yk plus 1, uk plus 1, and then xk plus 2. But this three-line description is a description of an iterative algorithm. So preceding the yk plus 1 update, there has to be an xk plus 1 update. So we can imagine the xk plus 1 update being written here with the same expression as the xk plus 2 update, except with the indices decremented by 1. So if we put the xk plus 1 update here and then remove the xk plus 2 update that following the uk plus 1 update, then we get this. So we have xk plus 1, yk plus 1, and then uk plus 1. So then we reorder the updates and then we cut the iteration so that each iteration is defined by an x, y, and then a u update rather than a y, u, and then x update that we had previously. And now if we examine the updates, the dependencies are in correct order. So preceding the xk plus 1 update, the uk and the yk updates have been computed, and that's utilized in the computation of xk plus 1. And then once xk plus 1 is computed, then the yk plus 1 update utilizes the uk update, which was computed here, and then the xk plus 1 update, which was computed here. So the dependency is correct. And then the uk plus 1 update relies on uk, which was computed here before xk plus 1, and then it utilizes the xk plus 1, the yk plus 1 iterates, which were computed in these two steps. And then finally, we can replace the objective here, this minimization problem, as the minimization of the augmented Lagrangian with yk and uk plugged in, and with x left as the free minimization variable. The reason these two minimization problems are equivalent is that the augmented Lagrangian and this objective, they only differ by terms that do not depend on x. This update can also be replaced by something involving the augmented Lagrangian, in particular the augmented Lagrangian with xk plus 1 plugged in, uk plugged in, and then y left as the free minimization variable. Again, this augmented Lagrangian and this minimization objective, they only differ by terms that do not depend on y. And finally, this dual variable update is clean as is, so we leave it. This method is referred to as the alternating direction method of multipliers, often abbreviated to ADMM. Okay, so we derived the ADMM method using the IPC technique. And this derivation, through this derivation, we have basically completed the core of the convergence analysis. What remains, however, is the careful bookkeeping. So we need to check conditions and translate the convergence of the DRS FPI into convergence of the ADMM method. So when we applied DRS to this unconstrained minimization problem with these two functions. Our convergence analysis of DRS requires total duality between this primal problem and this dual problem generated by this Lagrangian. So note that this is exactly the same dual problem as we had described before, but this primal problem is not the same primal problem as we had initially, the one with the linear equality constraint and without the IPC functions, but rather this is equivalent, but not the same, to the initial primal problem that we had. And consequently, this Lagrangian that generates this primal problem is also not exactly the same as the Lagrangian that generated the original primal problem. Interestingly, so this augmented Lagrangian, the L tilde, if we compare that to the other Lagrangian, the original Lagrangian L, the two Lagrangians, they generate equivalent but The two Lagrangians, they generate equivalent but slightly different primal problems, but they generate the same dual problem. In order to establish convergence of the DRS FPI, we need total duality with the Lagrangian L tilde rather than L, because we are applying a DRS to this primal problem rather than the original primal problem. It turns out that total duality with L tilde is equivalent to total duality with our original Lagrangian L. So in the end, there is no need to distinguish the notion of total duality with this Lagrangian compared to the total duality of this other Lagrangian. But a priori, that's not clear. So we at least initially make this distinction in order to apply the convergence analysis carefully and rigorously. Okay, now let's return to the original primal dual problem pair. So this is the original primal problem of the for ADMM, and this is the original dual problem of ADMM. Now, if the primal problem has solution x star, y star, and the dual problem has solution u star, and if strong duality holds between these primal dual problems, in other words, if total duality holds on the original Lagrangian L, if total duality holds on the original primal dual problem pair, then using a primal solution of this original primal problem, we are able to build a primal solution to this equivalent primal problem. The solution, the optimal z, is equal to a times x star. The optimal dual solution is the same because the dual problem is unchanged. So ax star and u star, that constitutes a primal dual solution pair for this equivalent primal dual problem pair. And because the optimal value given by this solution is equivalent to the optimal value given by this solution for the original primal problem, so to put it differently, the p star of this primal problem is the same as the p star of this primal problem. And the dual optimal value for this problem is the same as this problem because they are exactly the same problems. Therefore, strong duality also holds for this equivalent primal dual problem pair as well. So to conclude this line of reasoning, total duality of the original problem, so total duality with respect to L, the Lagrangian L, implies total duality of the equivalent problem. In other words, total duality of L implies total duality of L tilde. By the way, the converse implication is also true, but we don't need that direction of implication, so we won't argue and we won't prove that direction. So if total duality between the original primal and dual problems, so this primal dual problem pair, holds, and if the regularity condition that we had discussed holds, if alpha is positive, then the ADMM method is well defined and the method converges in the sense that a times xk converges to ax star and b times yk converges to by star. So to summarize our line of reasoning, we had an original primal problem, but we transformed the primal problem into an unconstrained equivalent primal problem. We applied DRS to the equivalent primal problem and then performed some change of variables to obtain the method ADMM. Then, in order to analyze convergence, we assumed conditions that would ensure the convergence of the DRS FPI, and then translated the convergence result of the DRS FPI into convergence of this equivalent ADMM method. But in order to ensure convergence of the DRS, we needed total duality, but it is more natural for us to assume total duality in this original primal dual problem pair rather than this equivalent transformed primal dual problem pair. So we established that that total duality of this primal dual problem pair implies total duality of this equivalent primal dual problem pair, and that in turn implies a convergence of the DRS FPI. Now here, I said that ADMM is well-defined under these assumptions. More specifically, ADMM is well-defined as a consequence of the regularity conditions discussed previously. Now, let me clarify what that means. So when we introduced the ADMM problem setup, we assumed certain regularity conditions regarding the range of A transpose, the range of B transpose, and then intersecting that with the relative interior of the domain of F star and G star. Now, these regularity conditions are necessary in the sense that they're used to ensure that the IPC of F by A and the IPC of G by B are CCP functions, and that the minimizers defining the iterations exist. So if we remember, The ADMM method is described in the end through the minimization with respect to the variable x and the minimization with respect to the variable y. Here, we're using the inclusion notation, so we are not asserting that the yk plus 1 and the xk plus 1 and the yk plus 1 are defined uniquely. In many cases, the minimizers are not unique. But in any case, we are assuming, implicitly at least, that the minimizers do exist. If these minimizers don't exist, then the ADMM method becomes undefined. Through the assumption of these regularity conditions, we are able to ensure that the minimizers defining the iterations, that they do indeed exist. Now, I will clarify that what I just described is a description of how we used these regularity conditions in order to establish convergence. But this explanation is not claiming that these regularity conditions are fully necessary. It turns out that the regularity conditions can be somewhat relaxed, and this is a topic that we'll discuss further later in the ADMM chapter of this book. Next, let's briefly step away from the lecture content to solve two exercise problems. Specifically, let's together solve exercise 1.6 and 3.1. Exercise 1.6 is entitled Existence of a Minimizer with Slater. The problem statement goes as follows. So let f be a CCP function on Rn, and then we let A be an m by n matrix. We assume that the range of A transpose intersects with the relative interior of the domain of f star, so we assume this regularity condition. And then we consider this optimization problem, this primal optimization problem, which is generated by this Lagrangian. And then the goal of the problem is to use Slater's constraint qualification to show that this minimizer exists. So the argument of this function is not empty. Note that in this primal optimization problem, we have variables mu and nu. So, and we assumed this regularity condition. Since we have f star here in the objective, this regularity condition ensures that Slater's constraint qualification holds for this primal minimization problem. Let's solve this problem. So the dual problem that's generated by this Lagrangian is given by, well, we take the Lagrangian, we minimize with respect to mu and nu. And when we do so, well, the Lagrangian splits into two terms, one term that depends on mu, the other term that depends on nu. So we perform this minimization with respect to mu to get this quadratic. We perform this minimization problem with respect to nu to get the conjugate of f star, which is equal to f because when f is CCP, f star star is equal to f. So this minimization becomes this supremum, and that becomes equals to minus f minus 1 over 2 ax minus y. So we have the sign difference because the dual problem is a maximization problem, but we recovered this minimization problem for which we want to show the existence of a minimizer for. So far we've established that for the primal optimization problem, Slater's constraint qualification holds. And we've also established that the dual optimization problem, the dual maximization problem, is in the form that we want it to be, and we want to show that the dual problem has a solution. Remember, what Slater's constraint qualification tells us is that if Slater's condition holds for the primal problem, then strong duality holds. And if the dual optimal value is not negative infinity, then furthermore, a dual solution exists. So it remains to show that the dual optimal value is not infinity. In other words, that d star is strictly bigger than minus infinity. Well, since the function f is proper, if you look at the dual objective, any feasible point f will yield a finite dual objective value. So because the dual problem is feasible, then we know that a d star is bigger than infinity. So therefore, combining this, the fact that d star is bigger than infinity with the Slater's constraint qualification for the primal problem, we can conclude that a dual solution exists. So the maximization with respect to f of this objective, this concave objective, has a solution. In other words, this minimization problem has a minimizer x. Next, we have exercise 3.1 entitled Procs of Infimal Postcomposition. Let f be a CCP function on Rn, and let A be an m by n matrix. we assume the regularity condition, the range of A transpose, intersects with the relative interior of the domain of F star. And then under this assumption, the goal of the problem is to show that the proximal operator with respect to the Infimal postcomposition of F by A can be evaluated by first performing this minimization with respect to X, and then computing the matrix vector product AX, and then assigning that to be equal to Z. And when we write down this formula, we also want an assurance that this argmin, this minimization problem, has a solution. Note that this minimization problem and this regularity condition is what we had considered previously in exercise 1.6. And exercise 1.6 immediately ensures that this argmin always exists. Now, this problem comes with a hint, and the hint states that to use exercise 1.6, as we just did, and furthermore to show that this minimization is equal to the proximal operator with respect to the IPC of F by A. Let's solve this problem together. So again, exercise 1.6 ensures the existence of the argmin. In the next step, we start with this, which was given in the hint. So we perform, and let's perform some calculations. So here in the inside, we are performing a infimum, a minimization with respect to X, subject to the linear equality constraint AX is equal to Z. So since AX is constrained to be equal to Z, we can always replace any instance of AX with just Z. So we do so here. So AX is replaced with Z. Everything else remains the same. And now, within the objective that we are minimizing with respect to, only the first function, f of x, explicitly depends on x. So we can perform the minimization with respect to x on just the first term. And since this is a minimization with respect to this linear equality constraint, well, we get the IPC of f by a by definition of the IPC. Now the z variable remains in this argmin, but now we have this form. This is in a familiar form. This is the proximal operator with respect to the IPC of f by a, with y provided as the input. Okay, so the goal was to show that this thing is equal to this thing. Well, we've established that this argmin with argmin inf is equal to the proximal operator. So it remains to show that this left-hand side can be evaluated by performing minimization with respect to x first, an unconstrained minimization with respect to x first, and then performing the matrix vector product AX. So to do so, in general, let's consider this form, where we perform an argmin of z and then an inf of x with respect to with the constraint AX is equal to z of a function h, where we assume that the argmin of h exists. Okay, so in this case, the optimization variable z solves this argmin. It solves this optimization problem if z is equal to ax and x is the argmin of h, because we have this inequality. So the infimum of over x, z, and x of h plus this indicator function, well, this infimum is the minimum objective value you would achieve with an optimum z. So the argmin z solves this optimization problem. But this objective on the inside is lower bounded by the infimum of h over x, because this objective has h and then this delta. But delta is 0 or infinity, so it's lower bounded by 0. So h is always lower bounded by h itself. And on the right-hand side, if we take the infimum over x and obtain the smallest possible value of h, well, the left-hand side has to be lower bounded by this quantity. This inequality will hold with equality if it is the case that z is equal to ax and x is equal to x is an argmin of h. Because if x is an argmin of h, well, if that is the case, we set z to be this value, and then this particular argmin of h will satisfy the constraint z equals ax. So when we plug in those values into here, this indicator function will be equal to 0. And then the objective value h will equal to, well, the argmin of h. So if in this case, this particular z is optimal for this optimization problem, and therefore it will be an argument of this.